In this video I'm going to build a very simple 4-ply laminate from unidirectional carbon fibre reinforced epoxy and look at the stiffness calculations that we can do using Autodesk Helius Composite. Let's just make sure we've got the correct units set here. File Preferences. Let's use the SI Units option here. So our laminate is built from layers of plies. In Helius these are called laminars. If we open the laminars tab here, we can see quite a big database of alternative materials which we can use as the building blocks for our laminate. Some of the names you'll recognise, some of the numbers perhaps you won't. Here's glass, boron fibre, graphite fibre, and so on. Also some materials which aren't obviously composite. There's steel and aluminium, which we could also include in our calculations if we wanted to. I'm going to build a laminate using unidirectional carbon epoxy, and I'm going to use this one here, T300 976. We double click on that, you can see the layer properties. These are the sort of moduli we would expect from a unidirectional material. 135 gigapascals in the fibre direction, 9 gigapascals at right angles. Notice that the layer data is in 3 dimensions. There's a value for E33 as well as E11 and E22, and we have 3-dimensional Poisson's ratios here as well. These greyed out boxes are used in thermal and moisture absorption calculations, so we don't need those for the moment. We'll consider these numbers later on as well. These are the limiting stresses that the ply material is allowed to take, and these are the limiting strains. We use these numbers in strength calculations, and as I say, we'll come back to that a little later on. You do need a number in the density box as well, otherwise the calculation won't proceed. We can create our own ply materials, and again we'll look at that in a later presentation. So let's make a laminate. New laminate. Let's give this a name, cross ply demo, and let's add one layer. That layer has to have a layer material, a laminar, so we'll select from all the ones available. I was using T300 976, so we select that. That ply now needs a thickness 0.125 of a millimetre. Do pay attention to the units here. We're in strict SI units, so these are in meters. Let's have this ply at 0 degrees. Let's repeat that layer, but change the orientation of this layer to 90. Now I'm going to select both of those layers with Control click and make the laminate symmetric. On the right you can see there's a nice little visualization of what we've created. 0, 90, 90 and 0. We'll save that laminate. Now we can look at laminate properties. In here is the mathematics of calculation of properties, which we don't concern ourselves at the moment, so we can go straight to the Properties tab here. Nothing appears until we press the Calculate button on the right, and we have 2 boxes of properties. One refers to 2 dimensions and the other to 3 dimensions. For classical laminate analysis we only need the 2-dimensional properties. The 3-dimensional properties might be useful if, for example, you want to work out some effective engineering properties and put those into, for example, a finite element calculation. So here are the effective in-plane elastic moduli, about 72 gigapascals in the X and Y directions, the in-plane shear modulus, and the in-plane Poisson's ratio. We also have bending moduli here. EXB and EYB are the moduli that we would measure if we did a bending test. You can see that they're not only different from the in-plane tensile moduli, but they're different in the X and the Y directions. And if you're in any doubt as to why that is, just go back to the way in which we built our laminate and make sure you can explain why the bending stiffnesses are different from the tensile stiffnesses, and also why they're different in the X and Y direction.